So hello everybody, today we are going to talk about how we can use Keras to implement neural networks for our projects. So we are using a data set that again it was part of a Kaggle competition, and you can go ahead and download it from Kaggle website, or we provided the data in our OWL website under the resources section in Unit 5 videos materials. So you can either make your own account and download it, or you can take it from OWL. However, we don't put it inside GitHub because it is quite heavy. It's about 2 gigabytes, and it was really difficult to upload it there. So the idea is that we have lots of credit card transactions, and we know most of them are legitimate. However, a very small amount of them are unlawful and fraudulent transactions. We want to make a model to be able to detect these transactions, and so that we can stop them right away. This is quite easy to believe that most of the transactions are actually legitimate, and we are dealing with very, very small amounts, maybe about 0.2% like wrongful transactions. This means that our data is very, very imbalanced, and that makes it quite difficult to train a right model. This is really good to know that we prefer to make a model to be able to flag or catch as many as these fraudulent transactions as possible. And if in this way we have to pay a price of flagging some legitimate transactions as like fraudulent, it's a price we are willing to pay, because this is really, really important to make sure that we find those fraudulent ones. So this is the whole idea and what's happening here. You can go to Kaggle website and see more description about this data set. As usual, at first we are going to import the libraries we are using. And then I'm using Keras for the deep learning part of the work. I put the explanation for Keras, and I put their documentation too. In summary, you can use Keras to build your neural network, and to be able to run Keras, you need something else called TensorFlow. But at the end of the day, if you install these two, you just need to write this one thing here. And after after importing all of your libraries, there is one more library that we are introducing today, and this is a Numpy library. Numpy is very handy when we want to do some mathematical work. And again, I put the related websites for the documentation related to Numpy here. It is just good to know that whenever you want to do anything related to mathematics, Numpy can be very, very handy, and it is quite easy to use, and it will save you from doing lots of for loops. So let's start. As always, the first thing we are going to do is to bring our data. The data is saved in CSV, so I just need to do pd.read CSV, and remember that pd is short for this pandas library. And then I have my data. I can look at the data. For security reasons, we do not really know the real name of these features. We just know them as V1, V2, means for like feature 1, feature 2. The only features that they relieved their names to us is time, the time steps between different transactions, and the amounts. So how much money was used, and we have a class, which is the target. 0 means legitimate, and 1 means fraudulent. So we have we have 28 of these features. We don't know their name. We have amounts and we have time. So we have about 30 features. And as you see, the data set is quite huge. So out of these huge data set, we have less than 500 fraudulent transactions. You can see how small this ratio is. As usual of all training processes for supervised learning, we have to have our feature and our class or targets separated. So this is what I'm doing here. I have a target and I have a feature data frame here. And it is easier now to make these data frames to an array. It is more mathematically easy for us to deal with it. So that is the np.array part. So at first, I remember I have my data. So this data is a pandas data frame. I took class aside. So data class will give me the target values, which is a binary case of 0 or 1. And then I drop the column class. Whatever is left for me will be the features. So now I have target and feature data frame. I'm going to change them to a Numpy array, which is really easy. I just need to do np.array. So now that we have this, we have our data set. Another thing we need to do before doing any training is to put some part of data, split some part of data for training and some part for validation. In this case, I decided to put 20% of data for validation and use the other 80% for actual training purpose. So we saw before that scikit-learn pack gives us the helper function to do that. This is another way of doing this. Is we don't want to use scikit-learn. It just I said that I want 20% of data being separated. And then because I am working with Numpy array, it is really easy to do indexing. I'm putting the first 20% for validation and the other 80% for test for training. So this is this part of the work, which is quite easy. And after that, I need to think more about imbalanced data. So we realized that the problem was really serious in the case. And we know that we really like to find those ones in class, meaning that we want to find fraudulent ones or positive cases here. One way to be able to catch them is that we give them more weight. So I see that I put more weight to all the features coming from the targets that I know they are 1. So at first I count them to see how many I have 0 and how many 1 I have in our data frame. And after that, I assign a weight to them, which is really easy. I just do 1 divided by number of each class. Because the number of the class for count 1 or positive cases is bigger, this value will be bigger, meaning that I put more weight for this specific class. So now that we talked about this, before going to build our network, we have to do a bit of data pre-processing. This is a very good thing to do all the time, and the reason is that this is mostly for the cases that features have really different ranges. For example, one feature ranges between 0 and 1, and the other one from 1 to, for example, 1 million. If we don't do some kind of scaling, then it looks like that maybe the number 500,000 is much more important than number 0.9, because remember, one feature was between 0 and 1 and the other one was between 1 to 1 million. So these bigger numbers might affect our whole model, because we put more weight to these bigger numbers, whereas they are not necessarily more important. So it is really important, a good practice for us to scale all of these features, and there are different ways to do that. I'm using a standard scalar method within scikit-learn. Again, you can go ahead and read about different pre-processing techniques and the mathematics behind them. One very good place to look at is actually the scikit-learn documentary about them. Here I'm just using it. So at first I have to import the data pre-processing package, which I did it here. It is I'm using a scikit-learn pre-processing package, and I'm looking at a standard scalar. So now after that, I make my object here. And now the only thing I need to do is just to fit my data and transform to the new scale, which will be, so at first I make my object here, and then I do scalar.fit transform. So, and now the result will be the scaled value of our feature. So that is it actually for the data pre-processing here. We are looking at quite a clean data set where we don't have nans and nulls or invalid values, to make it easy for you guys to be able to only focus on the network part. But in reality, remember, most of data are not clean, and you need to put lots of time in data pre-processing part. But now let's jump to the neural network part, where we are using Keras. So if you remember from lesson, we said that what's happening with neural networks is that we have some layers. So the first layer is our input, and then from input we go to the second layer, third layer, to the output. And we called all the layers between the input layer and output layer are hidden layers. So it looks like we have what we want to do is like stacking all these linear combinations between layers, because from one layer to the other layer, it was, and if you remember, we use a linear map, and then and then we use an activation function to make it nonlinear. So if we want to translate this in coding, Keras provide us with Keras.sequential, meaning the way to stack layers from one to the other one. So in this way, I just use Keras.sequential, and then within this, I put my layers. So all the time, the first layer here will be the layer that accommodating the input. So all the time, the shape for this layer will be equivalent to the shape of our inputs. Here we had about 20 features, so it will, or maybe 30, I can't remember. I think it was 30, yeah, so that will be the shape of our input. And to go from this layer to the next layer, the activation function that we are using is rel. So there are different activation functions. I put all the documentations for them here that you can go and look. And this is actually one of the hyperparameters that you can play around. Remember, hyperparameters in each in our models are parameters that we are going to tune them. They won't be, they are parameters of the whole model, and they are not something that you're going to optimize for the part of the modeling, but they are something that we choose, and then we train for different hyperparameters, and we see which of them in evaluation gives us the best answer. So activation function is one of the hyperparameters. The other hyperparameter that you can see is a number of nodes, how many nodes we are going to use for each layer, and many more that I'm going to talk about them one by one. So here I put some layers, some hidden layers. All of them are connected using ReLU. And here you see another thing I use from one layer to another layer, which is called dropout layer. So when you are going from one layer to another layer in a network, normally they're all fully connected. Like for all the one node is connected to the all nodes of the next layer. And it's happening for all the nodes and all the layers. It turns out that these fully connected neural networks are really prone to overfitting. Again, remember, overfitting was the case when our model was working very well for training, but could not really give us good reason in the good answer in validation part. And it looked like that we are just fitting all the noise event. So one easy way to tackle this overfitting problem with neural networks is something called dropout, meaning that randomly we say that, okay, I don't connect all these layers from all these connections from this layer to this layer. I'm going to drop out some of these layers. For example, here, 30% of them. So again, this number, that how many of these connections you want to lose from one layer to the other layer, is a hyperparameter that you should decide which is the best. And this is mostly coming with some trials. So, and then at the end, I have my last layer. The last layer here, because it's classification, has a shape of 1, meaning that it is either 0 or 1, right? So it is a binary classification. And for that, we are using the activation function sigmoid. So, and we talked about sigmoid before, right? So now that we built our model, this is the architecture of our model, and you see how it looks like here too. It gives us the summary here, model.summary here gives us the summary of how the model will look like. Now we want to do training because we haven't done any training yet. We just build our our training, the model itself, the architecture of that. So remember, this is a classification problem. So the metrics that we use for evaluation are stuff like false negative, false positive, true negative, true positive, precision and recall. We already know all of these explanations because we already talked about them in Unit 2 and Unit 3 and Unit 4 actually. These are the metrics that we use. We do not need to calculate any of them ourselves. Again, Keras is doing this for us. So we just need to do keras.metrics. For example, false negative, and then false positive, and these things. So this is the block for evaluation part actually. So now we need to talk about the actual training. We talk about evaluation, which is next actually. So let's do stuff in order actually. Let's talk about model.compile. So this part of the code tells us which loss function we want to use. Remember, we try to minimize the error, meaning that we want to make sure that in the training we have a way to evaluate that we find zeros as zeros and ones as ones. And binary cross entropy is a method of that gives us this ability. I'm not going to talk about the mathematics behind this loss function, but I put a very easy link below. If anyone is interested, they can look for it. But for now, just accept it that when we have classification problems, binary classification, one loss function that can be used is binary cross entropy. So again, I said that when you do the validation for me, use these metrics here. And the other thing that is about the optimization, remember we want to optimize our weights. So the goal of neural networks was like we have these weights connecting one layer to the other layer, and we want to optimize them. And they are different optimization methods. Here I'm using Adam. Again, the explanation of all of them is provided as an optional thing in the paper I signed here for you guys to read. But in general, Keras itself provides different optimization options for you. Here I'm using Adam, but you can use many other options as well. And that's about it. One more thing is that, remember we talked about we want to put more weight on class 1. This is how I say that. I make something called dictionary, which gives me the class and weight 0, and then 1, the weights for 1. So now that I said that, okay, when I build my network, I decided for validation purposes, I want to have these specific metrics for evaluation actually. I decided which loss function I want to use. I decided what optimization method I want to use. Now we are going to do model.fit to actually start the training. So this one gets some parameters itself too. Let's talk about them. So the first 2 parameters are actually our X and Y. Remember, this is a supervised learning method. So I need my input and output for training. So train feature normal is my normalized feature values. And then this guy is our target. So what is batch size? I don't want to go ahead and because I'm iterating for the optimization problem, I don't want to go ahead and in each iteration look at the whole data set, because it's a huge data set and it will make the process really slow. And instead of that, in each iteration or so-called epoch, I'm going to look at, for example, 2000 of these. Again, this number is one of the cases of hyperparameter tuning for you guys. So again, here is epoch, is the number of iterations. So how many iterations you want to go. Here I put 30. This is one of those things that you need to think about it. And there are actually some ways to visualize and see if 30 was enough and you would see this convergence rate or not. For now, I just put 30, but this is another hyperparameter. Again, there are ways of visualization. If you guys are interested, you can look for them that help you and see that, okay, after 30 epochs, for example, it looks like that I'm converging. And then we pretty much are good to go. The other parameters are quite easy to understand. And I just ran it before because it takes a bit of time. Maybe it took my laptop 2-3 minutes or maybe 5 minutes to run it. Then I can see for each of them, it gives me the loss value, false negative, false positive, true negative, and true positive. This is for the training part. And I get the whole thing for the validation set too. So it looks like that we have, in the last epoch that I'm looking at, we have false positive of 735, false negative of 10, true positive of 65, and true negative of 56,000 and something. So remember, we are really interested to find the positives. And it looks like that we are catching a good amount of them. We only missed 10 of them, and we found 65 of these true positives, which is really good actually. But we paid a price by flagging a lot of legitimate transactions and as wrong ones here, as like fraudulent ones. in reality, what people do is like even putting more weights on the positive classes, which may lead even in higher number of false positives. But remember, because this will be more expensive for us to miss true positives rather than false positives. So this is something that we are willing to do. This code is not optimized in many senses. None of these values here are checked, like maybe 256 nodes are not the best values. Maybe dropout of 0.3 is really big. Maybe ReLU is not the best activation function. There's a good chance that if we do a good hypertuning, these false positive values go down, actually, which might be a practice that you guys might be interested in do it. But in general, you can see that implementing neural networks using Keras is quite easy, and the code is really, really short. There are many, many good documentations for Keras. And actually, the example I gave here was one of the examples within the cross documentation as well. That being said, it means that Keras itself provides you with very good explanations and tutorials and examples, and is really, really recommended for you guys to go and look at them as well. So I hope that you enjoyed this lesson. See you later. Bye.